Phasor is a complex number that represents the magnitude and phase angle of a sinusoid. For example, we have the Im e to the j phi. That's a phasor that represents the amplitude and phase angle. So we use a bold-faced I to represent this as a phasor. Now, for handwriting, it's hard to make a bold-faced, so I'm going to have a double strike to represent phasor. And frequently, instead of writing as the exponential form, we only need to remember this: there is amplitude that we're interested in, and phase angle we're interested in. That is called phasor. And now we want to compare the function in time domain and frequency domain. And you can see here from the previous example, everyone would carry the omega t. If the source is driven at omega t, and the solution would have to have also the omega t, and that is not going to be changed. So this is not something that we need to worry about. What we do need to figure out from the previous example, that we use two different approaches, and we find that we need the magnitude, the Im, and we need to find the phase angle. So this expression is what we call a frequency domain, that we're not really interested in that omega t. So if we do the comparison, and we're going to draw a form. And we say, if in time domain that we have a function that is a times cosine omega t plus or minus a theta, a phase angle. This is a function, the time function that we ordinarily would see. If we want to express that in terms of in frequency domain, that we're only interested in the amplitude and phase angle, and that's a phasor, we would express that into amplitude and phase angle, then plus maybe or minus, depending on what is the given. If the function that is cosine function, be very careful. That we need to first convert sine function to cosine function. Remember, when we do that, the sine function, sine omega t, is equal to cosine omega t minus 90 degrees. So therefore, after we convert that to cosine function, so we wanted to make sure we need to convert it to cosine function. And we're going to end up with the same amplitude, of course, but the phase angle would be whatever the original phase angle here is, but we need to minus 90 degrees. Minus 90 degrees coming from the conversion from sine to cosine. So this is the conversion, and we can always write in, after we find the solution, that we find the amplitude, we find the phase angle, we can always express that back into the time domain. For example, we figured out I, and with Im, we figure out the phi. We can always write the solution to be I t is equal to the Im, the amplitude, times cosine omega t plus phi. What's the advantage of doing that? So we're going to do it one more time using that differential equation. That differential equation, that if we still remember, is L di dt and plus R times I is equal to Vm cosine omega t. Remember, this is the equation we obtained from the circuits by using KVL. Now we wanted to write in the phasor form, L times di dt di dt. The I, we're going to do the phasors. And the phasor contains only the information of amplitude and phase angle. So we're going to actually also, the I itself has that e to the j omega t component of it. That plus the r times I, again, the I is the phasor here and has the time function component of it, and that is equal to V. And V is just the phasor V because it contains everything here. Now, before we drop off the everybody has e to the j omega t, we need to take derivative first. And that ends up with j omega L and I itself, then multiply by e to the j omega t. And then we pretty much carry everything here. And you can see from there, we have e to the j omega t, e to the j omega t, e to the j omega t. So we end up with a phasor form. And so the phasor looks like that I times r plus j omega L is equal to phasor V. And quickly, we will have I is equal to the phasor V divided by r plus j omega L. And that is equal to I am phi. That's phasor I. Now you can see from there that the V phasor V, the phase angle is 0. So we have V m. The phasor angle here is e to the 0 divided by r plus j omega L. That, remember what we did earlier, we're going to have the same thing here. We have e m, e to the 0, and divided by r plus j omega L, and multiply by r minus j omega L. Now you can see we carry through the same thing. And we eventually, repeating what we have just finished earlier, and that gives us that V m e to the 0 divided by square root of r squared plus, remember we know where this is coming from, omega squared L squared, and e to the j of the phi is tangent, inverse of tangent omega L divided by r. So this negative of omega L divided by r. Now you can see in the phasor form it's much more condensed. This is the whole entire process. And therefore you can see we can just deal with the phasor relationships. And we're interested in only the amplitude and phase angle. So let's look at the example first. And we wanted to get familiar with the phasor, the transition between time domain to frequency domain. Then we keep on carry on how to deal with phasors. Now, the first example here is that we want to convert the following voltage functions to phasors. We have V1 that is equal to 9 times cosine omega t minus 125 degrees of volts, and D2 is equal to 18 times sine 377 t plus 45 degrees of volts. and we want to convert this function to phasor, we remember that this phasor is defined based on cosine function. So V1 directly, the phase angle just equal to negative 120 degrees. So V1 phasor is expressed in terms of 9 is the amplitude, and phase angle is negative 125 degrees in volts. Now for V2, what we have to do though is we notice this is a sine function. And first thing we need to do is we have to convert that V2 from sine to cosine. So that's the 18 times the cosine of the omega is 377. By the way, this is the omega, which corresponding to the frequency is equal to about 60 hertz. T. And then plus 45 degrees. And remember, we need to minus 90 to convert to cosine. So the phase angle now, based on the cosine function, the phase angle is negative 45 degrees. So V2 in this case is 18 as the amplitude phase angle is negative 45 degrees in volts. So this is the conversion. Here is an example for you to do. We want to convert the following function to time domain. The time domain that we're giving you the frequency is 400 hertz. And so what we need is that we need to remember that omega is equal to 2 pi f. So now you can convert it back because you know the amplitude in volt. This voltage here is in volts. And you know the omega now. And you can convert back from phasor to time domain. And the answer here is equal to V1 is equal to 12 amplitude cosine omega t, which is equal to 2 pi times 400, which end up with 800 pi. And the unit should be radians per second. So that will be 800 pi t. And the phase angle is 430, so that's plus 30 degrees in volts. And that's the solution to this problem.